much for putting together this great workshop. I'm learning a lot of things. Many of them outside of my expertise, I have to say. Yeah, it's so the topic of the talk is going to be some kind of connections between number theory, spectral geometry, and conformal field theory. And because I feel like what I work on is maybe it's not a different direction than what most people in this workshop are working on, I wanted to kind of start by a slide where I place this talk into the broader into the context of what's this conference. Right. The main topic is, of course, conformal field theory, and one of the main approaches, most successful approaches to conformal field theory is the probabilistic approach, whose goal is to rigorously construct the probability space, so the path integral, and starting from the definition, you want to prove that it satisfies the kind of the CFT axiom, so that it satisfies conformal symmetry and crossing symmetry, or the Siegel axioms more generally. And this is of course a very important goal, and there's been some impressive progress in some examples in 2 dimensions. For example, we heard a talk by Ante, and this progress is due to many people actually in this workshop. But one of the drawbacks, or one of the shortcomings so far, is that it seems to be very hard to carry this out in full generality. So, in particular, it's really out of reach for many models of interest, especially more than 2 dimensions. For example, the 3-dimensional Ising model at the critical point is supposed to be conformal invariant and crossing symmetric, but we are very far from constructing it rigorously and actually proving that it has these properties. So then there is an alternative approach to conformal field theory, which also works in general dimensions, which goes under the name of Conformal Bootstrap. And here the philosophy is a bit reversed. So instead of trying to prove conformal symmetry and crossing symmetry from some more elementary definition, you elevate these to some kind of principle. You kind of elevate these principles to axioms, and you formulate a definition of a CFT in general dimension, where the conformal invariance and crossing symmetry are built in, and then you can try to prove theorems starting from this definition. And what's very nice is that, like, over the last maybe decade or 15 years, people have realized that this approach seems to be very powerful also in higher dimensions. So in particular, it leads to some rather strong bounds on scaling exponents and the OP coefficients in generally. So this goes back to the work of Rychkov on the 3-dimensional Ising model. And it's really, in principle, even though it's been practiced by physicists, it's really as rigorous as I mean, it really is rigorous mathematics. You could make it into rigorous mathematics if you wanted to, but you have to assume conformal invariance and crossing symmetry. And here it's nice. It's very general, but the drawback is that you don't really know which objects this definition is describing, right? Because you haven't really proved that the 3D Ising model satisfies the definition, so you can't really be sure that the critical point of the statistical model actually satisfies the definition. But okay, that's something to keep in mind. And in this talk, I'm going to be working on describe a context where somehow both of these 2 drawbacks are avoided. So what I'll do, I'll formulate an analog of the conformal bootstrap, but not for conformal field theories, but for spectral theory of automorphic forms. And what's nice in this case is that conformal invariance and crossing symmetry are manifest, so you don't have to work very hard to prove that they're true. And therefore we can use all of these nice methods from that people have developed in the conformal bootstrap, this linear programming, symmetric programming methods, and so on, that people have used to bound exponents in the 3D Ising model. Here you can use them rigorously to prove properties of automorphic forms. So the summary is that you'll be able to use bootstrap methods to prove new theorems in number theory and spectral geometry. So that's somehow the context of the talk. So I wouldn't really be talking too much about CFTs, but there will be some strong similarity with what people are doing in CFTs. So the starting point, or the kind of main idea, is that there's this connection, there's this kind of analogy or similarity between 2 subjects. One is the subject of conformal field theory, now in general dimension. So the Versor algebra will make no appearance on one side, and on the other side, the spectral theory of automorphic forms, which I'll review. I'll explain what I mean by that. And I just want to, okay, so this connection goes back to this paper that I wrote with Peter Kravchuk and Sridhar Pan a few years ago. And so why should there be such a connection? The main idea is that both sides are very, very deeply rooted. I don't think I need this. Both sides are deeply rooted in unitary representation theory of non-compact Lie groups. So in conformal field theory, there are two very important semi-simple non-compact Lie groups which play the central role, which is the Euclidean conformal group SO1, D plus 1, and the Lorentzian conformal group SO2, D universal cover. And really everything in the subject is controlled by representation theory of these groups. So of course in 2 dimensions, this group is SL2R times SL2R, piece of the algebra, and this one gets enhanced to Versor times Versor. It is in this sense that these statements generalize the 2-dimensional case. And in the case of automorphic forms, the classical subject of automorphic forms is based on the group SL2R, so this was work of Poincaré for automorphic forms on the upper half plane. But then more recently, mostly due to the work of Langlands, it was realized that one should really consider automorphic forms over general semi-simple or general reductive groups. Okay, so like I already mentioned, then because of this connection, one can use the conformal bootstrap ideas to give some new rigorous results in number theory and spectral geometry. And what I'll talk about today is two classes of such results. The first one are bounds on spectral gaps of hyperbolic manifolds. And the second one are some new subconvex bounds on L functions. I'll explain what I mean by all of this as I go on. And the long-term goal is to kind of use this connection also in the opposite direction and use what we know, all the great things we know about automorphic forms, to use them as to give insights into conformal field theory. Just to give you an idea, this is something very, very concrete. There's kind of a simple dictionary between objects on the two sides that I'll elaborate on as I keep going. Really the main quantities that this subject is about are some kind of spectral data, where on the side of conformal field theory, the spectral data are the scaling dimensions of primary operators, so delta I. So this is the spectrum because it's a spectrum of the Hamiltonian on the sphere, or S1 in the 2-dimensional case. And the other piece of spectral data are the structure constants of the OP, so the 3-point function, CEA-Saclay. And on the side of automorphic forms, as I'll explain, they map to, the scaling exponents map to Laplace eigenvalues, also a natural notion of a spectrum basically of the Laplace operator. And the structure constants map to integrals of the product of eigenfunctions. The eigenfunctions, multiply them together and integrate over the manifold, you get some CEA-Saclay.
The limit?
Yeah.
Sorry, so in the case of the light limit of Liouville theory, I think such an integral of products of eigenfunctions was essentially computed by the Zablotchikovs in '95 as well, right?
Yeah. So if I understand right, in that case, these are just the eigenfunctions on the hyperbolic space. In the case that you're describing.
Yes.
Right. So the hyperbolic space is a very simple example of a hyperbolic manifold where everything is computable. So it's some of the question that I'll be asking about are not so interesting in the case of the entire hyperbolic space, but you should really be thinking of quotients of hyperbolic space which are chaotic. So that's maybe
what dimension? You
said any dimension. Well, the connection to Liouville is through H3, but what I'll be describing is really general for SO1, D plus 1. You can think of hyperbolic space of ND. And okay, the reason why there is a connection to number theory, or one manifestation of the connection to number theory, is that there is a very nice formula due to Watson and Icino that relates squares of these 3-point functions to special values of L functions. So L functions, transfer function, and generalize the Riemann zeta function, and I'll explain more about this also later on. And so in Conformal Bootstrap, we have some methodology for bounding the spectral data, the deltas and the CIJKs. And thanks to this mapping, you can use the same methods to bound the things on the right-hand side. And the corresponding techniques, in the case of automorphic forms, sometimes are known to mathematicians, but it turns out that often they're actually new. So we'll be able to prove some new results. So maybe I can start for if there are any more questions about this kind of general outline.
So because I was late, sorry, is it for any central charge?
So there is no central charge in the stir because there is no Virasoro. Yeah, it's
okay, but you have those eigenvalues. So should I think about it as some limit, like the hyperbolic limit as an example?
Yeah, well, in the case I was mentioning about Liouville theory, it's the C equals infinity.
Yeah, I know. Yes.
Yeah, I think that to understand what I'm talking about is a bit misleading. So you should forget about Liouville.
Okay.
And I mean the base. Okay, maybe I'll go back to this slide. So the main idea is that one can formulate conformal bootstrap for a general semi-simple Lie group. Where the Lie groups which play a role in CFTs are SO1, D plus 1 or SO2, D. So in particular, in 2 dimensions, we would only be using the SO2, D.
I see.
Which is the global part of the Virasoro. So central charge makes no appearance. It's related to the classical limit of Liouville, where also the conformal blocks in a C goes to limit become the SL2 blocks. But you can forget about Virasoro. Any more questions?
So the delta i's are eigenvalues of what operator exactly?
Of the Hamiltonian for the theory quantized on the codimension 1 sphere in general. So on S1, so in a 2D conformal field it will be on S1. In general it will be S to D minus 1. And by state operator map, these are also the scaling exponents, scaling dimensions of primary operator. Any more questions? Okay, so here's a plan for the talk. Well, I already did a part of the introduction, and I'll review the connection in more detail. Then second part will be about using Bootstrap to bound spectral gaps of hyperbolic manifolds, which me and my collaborators have given quite a few talks about over the last few years. So this will be rather brief. But then there's some set of new results, which is about these L functions. So I'll explain how to prove some new bounds on these L functions, which is a work that will appear on the archive tomorrow. And finally, I'll describe some upcoming work of Angelo Abbe, who is a graduate student of Peter Sarnak, who proved some sort of completeness result for this bootstrap method for hyperbolic surfaces, which I think is very suggestive also for conformal field theory. But okay, before I explain that connection, I just want to take a bit of a detour and say a little bit about how one can think of quantum field theory. So what is quantum field theory? Well, in principle, it should be some kind of a measure on something like functions or distributions. You know, and these functions can be scalars, fermions, gauge fields, or some discrete features of freedom. And this measure can be rather far from the Gaussian measure in general. So this means that the theory is strongly coupled. Once you have it, you can talk about correlation functions by being integrals with respect to this measure. Now this measure is not just some arbitrary measure, and most important constraint that it should satisfy is locality, which is roughly speaking that it kind of factors over the points. Okay, this is not really a precise equation, but it's supposed to be a rough description of what locality means. Then you can talk about local operators, which are some random variables built out of these local fields in the infinitesimal neighborhood of a point. And the main purpose in life of these local operators is that you can use them to deform the measure in such a way that it remains local. So you can add this exponential of a linear combination of these operators to the measure, and this formula will preserve this locality. And then the space of conformal field theories, omega is just the space of these couplings, so space of these couplings you can turn on. And the most important observation is that once you rescale space-time, or space, it's equivalent to some redefinition of these couplings. So this is the notion of renormalization group. And the conformal field theories are supposed to be fixed points of this, action of the rescaling on the space of couplings. So that's how, at a physics level of rigor, would somebody define what conformal field theory is. And an important goal is to try to classify conformal field theories in general D, but of course this is basically impossible starting from the ideas from the previous slide at the moment, because there is really like no precise global notion of the space of couplings omega. Even if you can kind of define it in the vicinity of some conformal field theory by classifying local operators, there is it's not really well understood how it connects to the other description, like around other CFTs. And it's impossible to calculate what this RG flow looks like in the regime of a strong coupling. So while this definition of the previous slide is supposed to capture the physical essence of conformal field theory, it's not really mathematically that useful in general. But then there's an alternative approach, which is this conformal bootstrap, which is trying to define directly the fixed point without referring to general quantum field theory, which is this algebraic definition of CFT in general D, going under the name of conformal bootstrap. So here is the corresponding sketch of a definition of CFT in general D in the spirit of the bootstrap. Really, the main ingredient is a space of states. So this is some Hilbert space V, which is a positive energy unitary representation of SO2, D. So this is, if you prefer talking about two dimensions, again, this SO2, is really SL2R times SL2R, and it enhances to Virasoro times Virasoro. But this story with lowest weight modulus of Virasoro generalizes very naturally to higher dimensions. So the Hilbert space is a representation of this group. And the reason why this group plays a role is that this is the group of conformal automorphisms of the cylinder, so R times SD minus 1.
So your group acts only on the space, not on time?
No, on space-time. So the reason why this group is that the space-time is R times SD minus 1, so we are in D-dimensional CFT. And
you imagine it embedded into a sphere, or as D, no?
No. So it's a Lorentzian space-time. So the SO2, D is the group of conformal automorphisms of the Lorentzian cylinder. So you have a time going up and space being SD minus 1. So the space of states on SD minus 1 is the space of local operators by state operators.
So it's not a direct product. It's not a direct product.
Topologically or geometrically even, geometrically it's a direct product. You have a flat metric on R and the round metric on SD minus 1, but they have the opposite.
But this metric depends on time.
No. Well, up to Weyl transformation.
To scalar, but scalar depends on time.
Yeah. Well, in this picture it doesn't. So it's
This group is a group of conformal transformations of a quadric of something compact. That's what Volodya is saying.
I don't think. I mean, you need this universal card. So it's there are two most important spaces. One is the Riemannian round sphere SD. Okay. Then the group of conformal of that is SO1, D plus 1, and the other. And I'm not talking about that. I'm talking about a different spacetime, which is this one, which is now Lorentzian. So the R factor has the opposite sign than the SD minus 1 factor, and it's non-compact, and it's Weyl equivalent to the one punctured RD, where you give kind of a Lorentzian metric to the radial direction. And then you get this group, which is the group of conformal automorphisms.
And strictly speaking, SO2D will act on something compact, which is given by a quadratic equation.
Yeah, so SO2D acts on on the quotient of this by translation in this direction. But once you decompactify the R direction, you get a non-compact space, and the group that acts is the unit. That's why I have this twiddle. That's exactly to address that. Does that? It's okay. Okay, so then you can talk about a spectrum of irreducibles, which are the lowest weight representations appearing in this Hilbert space V. There are some infinite dimensional representations called delta rho. So delta and rho are the spectral data, where delta is the scaling exponent and rho is something called spin. There's a vacuum in this Hilbert space, which is just a trivial one-dimensional representation of this group. And the next ingredient is a state operator map, which is, okay, I won't describe it very precisely, but you can do it. The kind of sketch of a definition is that there is some kind of families of densely defined operators, phi I of x, which act on this Hilbert space in such a way that if you act with phi I on the vacuum, you span a dense subspace of this VI, of this irreducible factor corresponding to some primary operator. And once you have these operators, you can multiply them together, and your periodic expansion says that these phi satisfy some algebra that if you multiply them together, you can expand it in a complete set of these operators with structure constant CEA-Saclay. And the dependence on x and y is fixed by equivariance with respect to this group SO2, D. It's really important that when he's using this group SO2, D rather than the SO1, D plus 1, but I guess that won't make such an important appearance in this talk.
And it's important that this sum is discrete?
In most interesting cases, I think it's discrete, but it's not really important for for example, in Liouville, it's continuous, and that also works, but it's not that important. Okay, then there's an important empirical fact that this bootstrap definition of a CFT seems to lead to very strong constraints on the spectral data. Not any spectrum can appear in the Hilbert space, and in particular, people have derived rather impressive estimates on the scaling exponents in the three-dimensional Ising model. So at the moment, there are no 7 decimal places from the work, my paper from last year. I'm told that the authors have since added at least one more digit to these numbers. So this really just follows from the definition and some rough assumptions like only 2 relevant operators, there was equal symmetry and so on. So it's very impressive, but so this kind of suggests that the bootstrap definition knows a lot about actual physical notion of CFT, even though this is not guaranteed. So this direction going from physical CFT to bootstrap CFT is more or less uncontroversial, even though of course we know it's still hard to prove that some kind of RG fixed point is conformal invariant, but at least by physics tendency of rigor, this is not really usually questioned. But going in the opposite direction is much less obvious. So the fact that any solution of the bootstrap axiom should actually arise from physical CFT is not obvious at all. And if it's so, asking whether this holds is kind of like asking whether the bootstrap is complete, whether the definition knows everything about a subject. And if it holds, you can go from here to here, then we should be able to prove one day many amazing theorems about the subject of quantum field theory, starting from the definition of the previous slide. So there are various kind of folk theorems that people expect to hold based on a kind of RG definition of a CFT. So, for example, in 4 dimensions with any supersymmetry, the only CFTs that we know is the super Yang-Mills, the n equals super Yang-Mills, and it would be great to actually prove it rigorously that there are no other CFTs or for super Yang-Mills with this amount of symmetry. Or in more than 6 dimensions, there are some heuristic arguments that the only unitary local CFTs are free, and again, this is an important challenge for the bootstrap definition to actually prove it. But okay, all of this is some very far future. But what I'll talk about today is a context where you can prove the analogous theorem completely rigorously, and this was done by Adve. So what he proved is that this completeness notion holds for compact hyperbolic surfaces. So we can prove that the bootstrap equations that I'll talk about soon for hyperbolic spectra completely characterize hyperbolic surfaces. So much for the motivation. I'm already spoken for 25 minutes, so now I'll finally get to the heart of the talk. So, what are automorphic forms? So in general, they are associated to semi-simple Lie groups G. So let G be such a group, and let's take gamma to be some discrete subgroup of finite covolume. So such as the quotient of G mod gamma is finite. You can, for example, think of G being SL2R and gamma to be being SL2Z. Then G mod gamma, this quotient G mod gamma carries a unique G invariant probability measure. So this just descends from the Haar measure on G. And the space of functions on G mod gamma with respect to this measure, the L2 space, is a unitary representation of G, because G acts by translations on it. So, and okay, this of course preserves the measure, so this L2 space is a unitary representation of G, infinite dimensional. And okay, so even though this is not really strictly speaking needed, as I was answering to Jasper's question, we'll assume for simplicity that this quotient is compact, which then implies that it decomposes discretely into irreducibles. Right? So these VIs are unitary reducible representations of G. They are themselves infinite dimensional, and in this case, this Hilbert space decomposes discretely in an analogy with the Hilbert space of a compact unitary CFT on S1, on SD-1. Now to define automorphic form, let K be a maximal compact subgroup of G. And then an automorphic form is the function on the quotient G mod gamma which satisfies two things. So firstly, it should transform irreducibly under the maximal compact group, and it should also transform irreducibly under G. So these two are rather independent things. Irreducible under K means, roughly speaking, that F is just a function on this space. So, okay, if F transforms trivially under K, then F is just a function on this double quotient. So this is for example, this is a hyperbolic surface in the case when G is SL2R. And if it transforms irreducibly, it's just it's a section of some bundle over this manifold. And irreducible under G means that F is an eigenfunction of some system of differential equations. So it's basically because the central of the universal enveloping algebra of the algebra of G is generated by these Casimir elements, F needs to be an eigenfunction of Casimir differential operators. So that's okay. And these two statements together define what an automorphic form is. So, for example, holomorphic modular forms are examples of that, where these differential operators are actually first order. So they're just like the anti-holomorphic derivative. Holomorphic modular form is killed by the anti-holomorphic derivative.
Is it possible to give a simple example of the double quotient space?
Any hyperbolic surface is an example. So when G is SL2R, SL2R, K is SO2. So G mod K is the hyperbolic half space. And gamma is a discrete subgroup. So G mod gamma mod K is a quotient of the hyperbolic space by discrete subgroup of PSL2R. In other words, a hyperbolic surface.
Yeah.
Sorry, is it possible that the choice of K makes a difference?
No, all K's are equivalent up to conjugation, so there's no.
Even if there is a gamma, which it's that's right.
Okay, so actually this is the example I already answered to Elena. So this is the fundamental example of PSL2R. Here the case maximum Hilbert group is SO2. Gmod K is the upper half plane with hyperbolic metric. And gamma is a Fuchs-Stein group, so such that this double quotient is a compact hyperbolic surface. So here's some example of a genus 2 quotient where this black and white region is the fundamental domain for some particular gamma, and once you quotient you get a particular symmetric genus 2 surface. And then let's talk about the L2 of Gmod gamma. It decomposes discretely. In the compact case, there is the discrete summands take the following form. So let me just go through them one by one. The trivial representation, which is the only unitary one-dimensional representation of G. Okay, so I should say these are the irreducibles under PSL2R. Summands here. The trivial representation appears once. It corresponds to the constant functions. Then there is a so-called discrete series, D of n, which are the lowest weight representations, and they correspond to holomorphic modular forms of weight 2n. So they are functions on the upper half plane that transform as such under gamma. And these come together with their conjugates. So these are lowest weight, these are highest weight representations. And finally, there are these principal series representations, so P labeled by lambda, which are in one-to-one correspondence with Laplace eigenfunctions on the surface, where lambda is the eigenvalue of the corresponding Laplace eigenfunction. So it's kind of nice because the problem of solving the Laplace equation on some hyperbolic surface in this formulation is equivalent to a representation theory question. Like you take L2 of Gmod gamma, and the task of decomposing L2 of Gmod gamma into irreducibles is equivalent to finding the spectrum of the Laplacian on the hyperbolic surface and the spectrum of holomorphic modular forms on the surface. So the spectrum depends on gamma on the surface, but we'll see. It's all constrained by the bootstrap. So just a few more comments about the spectrum. So now I'm still specializing to the two-dimensional case. The spectrum of these holomorphic discrete series, or holomorphic modular forms, is fixed by the Riemann-Roch theorem. So in particular, it only depends on the topology of the surface. It doesn't depend on the moduli. And the multiplicity is just fixed by the genus. But the Laplace spectrum is much more interesting. It's chaotic in general, it's moduli dependent, and there is no closed form for it. So there is this connection to quantum chaos in the classical limit of, I guess this should be k going to infinity. And the main idea of this bootstrap method is that the spectrum is not arbitrary. It's highly constrained by additional structure, which is basically existence of a product. Of the fact that you can take two functions on the quotient, multiply them together, and decompose the result using the spectral decomposition. And the compatibility of the spectral decomposition with associativity with this multiplication implies rather strong constraints on the possible spectra that can appear in this decomposition. So the reason why this can be actually implemented is that, at least for PSL2R, if you think about a space of G equivariant maps from the tensor product of two irreducible representations to a third one, then this is typically one-dimensional, or zero one-dimensional, and sometimes two-dimensional. So it's at most two-dimensional. If at least one of these three, Vi, Vj, Vk, is a discrete series, it's actually one-dimensional. So the structure of the product is highly constrained by representation theory. So if you take two product of two functions and decompose them using the spectral decomposition, then this is the projection on the kth summand here, for example, the principal series. Then this projection is fixed by representation theory up to an overall constant, where this is just the analog of the OP coefficient of the three-point function. And this is some universal map, the unique up to an overall factor map from Vi times Vj into Vk. and is proportionally constant, no, that's something that's not fixed by representation theory, but it depends on a particular surface or hyperbolic manifold, can be computed in principle as an integral of a triple product of automorphic forms of these
Well,
F.
it's two-dimensional said that the space of G-invariance map is two-dimensional sometimes.
Sorry, can you?
Two-dimensional.
Oh, this space.
When it's two-dimensional.
When all three are principal series. Usually this is avoided by going to GL. So if instead of PSL2R you work with PGL2R, then it's one-dimensional. Yeah. So it's because I'm only using PSL2R.
We have heard the statement that the tensor product of two principal series representation doesn't depend on the factors. They are all isomorphic. If you take product of two irreducible representations, A and B, and you multiply, and then C and D, you multiply them, then these two products are isomorphic,
Yes.
independent on A and B.
Okay.
So therefore, the space of, well, somehow this doesn't depend on ING. This space of maps doesn't depend on ING.
Well, okay, as representations of PSL2R, they are the same, but of course the intertwiner which proves this is complicated, and the form of the intertwiner is very important.
Maybe some distinguished intertwiners,
Yeah.
but there are, in principle, there are many of them. Well, okay, but this is
Yeah. Maybe you can ask me again once I've explained it. Okay, so then what is it? Associativity or the bootstrap or the? Well, actually, it turns out that a similar idea of this associativity or the bootstrap in the concept of automorphic forms was discovered independently by number theorists, so by Bernstein and Reznikov under the name of specular reciprocity formula. And so here I give a presentation which is in that spirit. So that the idea is to now consider an integral of a quadruple product for automorphic forms, integrated over its quotient, and apply the specular decomposition in two different ways. So you can either apply it like that, to FIFJ, or to FIFK, say. In the first case, you get an expression for this I, which is bilinear in the structure constants, with some kind of universal object, I, which is really the analog of the conformal block, which is just this gluing of triple intertwiners, and it's completely determined by permutation theory. And associativity is just a statement that this thing should be permutation symmetric under IJ permuting IJKL, so you get this nice crossing equation which is bilinear in the structure constants and depends in some controlled way on the spectral data, which are in these conformal blocks. So it's usually represented in this way. And so you get some infinite set of equations for the infinitely many unknowns. So the equations are labeled by choice of 4 irreducibles, I, J, K, and L, and also by choice of these 4 vectors, Fi, which themselves range over the infinite dimensional space Vi. And the unknowns are the C's and the spectral data. So this is exactly in the same spirit as the conformal bootstrap. Is some infinite set of equations for the spectral data of conformal field theory. Okay, so that's basically the setup, and now I'll talk about some applications. Unless there are further questions. I mean, so maybe as an answer to your question, it's true that the two tensor products are isomorphic, but that doesn't imply that the conformal blocks are independent of I, J, K, and L.
And on the other hand, there is also this problem how to normalize these intertwiners. There is no canonical way to do that.
That's right. Yeah. So well, I guess it's a little bit like there's no if you redefine your intertwiners, you're going to redefine the CIJ case.
Yeah, but these are not canonically defined.
Well, on the side of automorphic forms, there's some kind of partially canonical normalization, which is that you want to normalize your eigenfunctions to have a unit norm. then this is, so this gives you some normalization of the CEA-Saclay.
Yeah, but you can multiply by phase.
That's right.
Always.
Yeah,
Phase you
that's
can
right.
always multiply.
Okay, so here's the first application, which I'll just be brief because, like I said, we've already I've given a talk at a similar conference a few years ago about this, so you were probably there, but I still will try to mention the important points. So just a summary of the main results in the case of hyperbolic surfaces. So one thing that follows from the associated formula is an upper bound on the spectral gap at a fixed topology. So for example, at genus 2, the upper bound on the spectral gap following from this bootstrap is this number. And remarkably, there is actually a genus 2 surface, some special point in the moduli space, which almost saturates it. So it's a Bolza surface, which is the regular octagon in the hyperbolic disk, whose eigenvalue is the same up to 4 decimal places. So this is quite nice that we have some universal bound that only uses the fact that the genus 2 is basically only uses the fact that there are 2 holomorphic 1 forms in the spectrum of holomorphic module forms, and just from that you get this number, and it agrees rather well with the.
I'm sorry, sir. What is orbifold actually? What is an orbifold?
Sorry. I guess I was talking about surface. Orbifold just means that gamma is allowed to have elements of finite order. So in general, the gamma, well, if you want it to be hyperbolic surface, gamma should only have hyperbolic elements. But everything that I said also applies in the case where there are elements of finite order in gamma, and then correspondingly the surface can have conical singularities.
So, and it can be arbitrary number of the singularities, or you fix it?
Well, yeah, there can be an arbitrary number subject to the fact that such a hyperbolic orbifold exists. Okay, so then another example of something that you can prove in the bootstrap, the genus 3, there's this upper bound 2.678, something, and this is almost saturated by the Klein quartet, which is a particularly symmetric genus 3 surface. And another question that we were asking is, what set of spectral gaps do you get when you vary gamma over all the co-compact subgroups of PSO2R, so basically all of the compact hyperbolic orbifolds, and this is the answer that we came up with using the bootstrap, or more or less just using the bootstrap. Just some explanation. So above the real axis you have the topological type. So topological type is labeled by the genus and the orders of the elliptic point. So that's partially an answer to your question. The orbifold just means that there are some elliptic points of these orders, and it also applies in this case. So for example, the maximizer of lambda 1 among all hyperbolic orbifolds is this 237 surface, which is also one of the minimal area. Then there are 2 more 3-punctured spheres, which are isolated, and then there's a continuum which is spanned by, with 4 punctures. You get a continuum because you can go, now you have a moduli space, you can take pairs of 2 punctures very far away from each other, and as you do that, lambda 1 decreases, and eventually it gets all the way down to 0. Right. I don't want to spend too much time describing it, because I want to get to the L function part. Okay, comments about the proof. There is some interesting connection to sphere backing and these extremal functions of Vyazovska and Conan-Elkis, which, again, I think I've given many talks about this, so I'll skip it. But then here is the result for hyperbolic 3 manifold. So there's really nothing too special about hyperbolic surfaces from my point of view. We can generalize it in principle, to NAD. We've only generalized it to 3D so far. And here's just an example result where on the 2 axes you have the spectral gap. On horizontal axis is the spectral gap on holomorphic, on vector fields, and on vertical axis the spectral gap on tensors of rank 2. The dots are actual spectral gaps computed using the Zelberg trace formula for particular examples of hyperbolic free manifolds. So now they are all isolated because most of rigidity tells you that these things don't have moduli. And the blue curve is an upper bound following from associated, so following from the bootstrap. And you can see nicely all of the hyperbolic free manifolds that we looked at nicely kind of span the entire region under the upper bound. It's a very universal upper bound that we can compute from representation theory of SL2C.
Sorry, so is there a meaning to the minimum of this curve?
Not really. I mean, not that I'm aware of. The curve is a result of some computation, and there's ultimately, because you need to optimize in some infinite dimensional space, this curve is a result of this optimization. So I don't think there is any particularly nice formula for the curve. There are some manifolds which come relatively close to the minimum of the curve.
And can this spectral gap be extracted from the spectrum of geodesics?
So that's exactly how we found it. That's spectrum of geodesics is relatively simpler to compute than the spectrum of Laplacian, so you can then feed it into the Zelberg trace formula to estimate the spectral gap. So that's how we computed these red points. Okay, there have been some additional developments. For example, one work of Fortier-Bork and Petri, who applied the trace formula directly to the spectral gaps, in sense of linear programming, as well as another work by Shestopal, Simonsdorf, and Shu on the spinner case on hyperbolic surfaces. But okay, so much about the previous work. In the final 10 minutes, I want to talk about L functions. So what are L functions? Well, the simplest L function is the Riemann zeta function, which is usually defined using the Dirichlet series, like that, and analytically continuing to general complex S. Its most important features is that it has this Euler product that it factors over primes with this factor 1 minus p to the minus s to the minus 1. And secondly, that it satisfies a functional equation under s goes to 1 minus s. So you need to multiply it by some gamma function, and then it's reflection symmetric. And one can define a general L function to be an appropriate generalization of the Riemann zeta function. So here's the definition. It's so an L function is first of all a Dirichlet series, which is this kind of object. So sum over integers of n to the minus s with some coefficients, which are some complex numbers. But these complex numbers are not arbitrary. They need to be such that 1 and 2 are satisfied. So 1 is Euler product, which is the analog of this product over primes, where now the L function is supposed to factor with these factors LP, where 1 over LP is a polynomial in p to the minus s of some bounded degree. So it's bounded for the entire L function. Here it's degree 1 in p to the minus s, but in general it could be some higher degree. And this is called degree of the L function. And secondly, L should satisfy a functional equation where if you multiply it by other specific gamma factors, then it satisfies a reflection symmetry under s goes to 1 minus s. All these gamma factors and the LP have a nice representation theoretic meaning, but I won't talk about that today. But the reason why I don't mention care about L functions is that many very deep results in number theory are very nicely captured by L functions. So many deep results in number theory either follow or would follow from various analytic properties of these L functions. So, for example, the prime number theorem, which gives you the asymptotics of the number of primes up to a given value, is a consequence of the fact that the Riemann zeta function has no zero on 1 plus it, and you're supposed to get the optimal error term by looking at by proving that there are no that the only zeros are at 1/2 plus IT, which is of course the Riemann hypothesis. And this Riemann hypothesis is a generalization to all L functions, going under the name of grand Riemann hypothesis. So that's just a statement that this L function only has zeros when the real part of S is 1/2. A particular consequence of the grand Riemann hypothesis is a so-called Lindelof hypothesis, which is the statement that the L function grows slower than arbitrarily small positive power of the argument along the critical axis. And this is a nice generalization to families of L functions. So if we have some family of L functions labeled by some invariant f, then this value should be bounded, according to the Lindelof hypothesis, by an arbitrarily small positive power of certain invariant C, which is called a conductor. So this is some kind of number which measures the complexity of the L function. And then it's relatively easy to prove using the functional equation, the so-called convexity bound, which is that this is bounded by a conductor to the 1/4. So let's say that for degree d L functions, this goes like t to the d. This is relatively easy to prove. And various important facts in number theory would follow if you can improve this convexity bound to a better exponent. So if you can reduce this 1/4, and in that case, it's called a subconvex bound. And this is a problem that worked on by various people going back to Harder and Middlewood, who first improved it, the convexity bound for the Riemann zeta function, and all the way until today for various families of L functions. And what we managed to do with Anshul Adve and a few physicists is to use this bootstrap method to in a very particular case improve the state of the art on these convexity bounds for L functions. So let me say in which context this happened and why you can actually use the bootstrap to do that. So the main ingredient that I haven't described yet is this formula of Watson and Icino, which says that if you have an arithmetic hyperbolic surface, then the 3-point function squared, so remember these are integrals of triple products of eigenfunctions, so in that case these numbers are proportional to certain L functions that you can build using the arithmetic properties of the surface, so in particular the so-called Hecke eigenvalues associated to the L function is a triple product L function, so it's something associated to 3 automorphic representations of SL2. So there's these PI, PJ, PKR automorphic representations of GL2. And in the case that we looked at, the three automorphic forms are a holomorphic one, anti-holomorphic one, and a Laplace eigenfunction. So this is also known as a mass form. And what we want to estimate to improve the convex bound on this L is the limit where I and J are kept fixed. So the holomorphic form is kept fixed, and the Laplace eigenvalue goes to infinity. So this lambda k becomes very large. And in that case, you can talk about the quality of a subconvex bound, sigma, which is some number between 0 and 1, where the L function should be bounded by this power of C, where sigma is just sigma being 0 is the convex bound, and a positive sigma is a subconvex bound. So it's equivalent to this bound on the OP coefficient at large k.
What is C here?
Which C? This C? C is the conductor of this triple of this L function. So it's some analytic conductor.
I have another question. So the convex bound was for like in the symptotic in the argument of the L function, and here the argument is fixed at 1/2, or maybe it's just a slightly different.
The C depends.
Yeah, so C in the general case of the previous slide depends both on T and on the automorphic representation.
Oh, so it's a limit in both T and...
Well, what we are proving is a special case of this bound where we keep T fixed. Okay, we keep T 0 in this case, and we are more interested in the growth of this number as a function of the family, where the family is labeled by the Laplace eigenvalue. But T is kept fixed in our case, but there are various important. In the case of the Riemann zeta function, it's only T that can vary, and that's what Hardy and Little improved. Okay, so now what was the state of the art before our work? Well, the most important work was that of Bernstein and Reznikov from 2010, who proved this bound with sigma at least 1/6 for general gamma. So not even arithmetic. They didn't even use arithmeticity because they really just used this specular reciprocity formula, or the bootstrap equation, as I was calling it. And then,
how you define L function if it's not arithmetic?
If it's not
arithmetic.
Yeah, so good. In that case, it's interpreted as a bound on the trilinear period on the CEA-Saclay. The connection to L function is only in the arithmetic case, but Bernstein and Reznikov proved a theorem about trilinear periods, which had a corollary.
And one more question: so how you normalize Fi, Fj, and Phi k?
Yeah, so in this case, they are all normalized to have a unit norm. And then in 2021, Blummer, Jana, and Nelson improved this Bernstein-Reznikov result to sigma, basically to twice as good, sigma being at least 1/3, but only for a very special gamma, so for SL2Z. And this value 1/3 is a rather critical threshold, usually called the Weil. Weil was the first one who gave like a sketch of an argument for the Riemann zeta function. And what we did is by essentially upgrading the method of Bernstein-Reznikov, we were able to get the same quality of the bound for general gamma. So not just for SL2Z, but even for non-arithmetic gamma. So that's the paper that should appear tomorrow.
Is this expected to be the optimal exponent, or is there?
Well, the optimal exponent is supposed to be Lindelof, so that's 1, but that hasn't been proved in any case. Even for the Riemann zeta function, I think the exponent currently known is like 1/3 plus some tiny fraction. That's due to Bourgain. So basically, in most cases, this Weil bound seems to be a natural threshold. And
so normally you truncate the spectrum to a finite number of fields, but here you want the asymptotics for k goes to infinity. So how do you do that?
No, let me maybe describe a proof, even though I'm running a bit short on time. Well, okay. Yeah, maybe just quick. The idea. The reason why you can say something about the large K limit is, of course, if you look at the 4-point function of these holomorphic forms. So the holomorphic forms are kept fixed, but if you apply the spectral decomposition to the product of two holomorphic forms, you're going to find the Laplace eigenfunctions of arbitrarily high Laplace eigenvalue. So it's like the OP of two fixed operators contains primary operators of arbitrarily high scaling dimension. Well, and I'm really running short on time, so feel free to ask me maybe after the talk about the specific method. But you may wonder how come that physicists were able to improve on something that mathematicians did, and that's a good question. And really the reason is that physicists like explicit formulas and explicit calculations. So our starting point was this very nice Recursion equation, which is very explicit Recursion equation where these H are some conformal partial waves, very explicit hypergeometric functions. So somehow our form of the specular reciprocity formula was much more explicit than the one that Bernstein and Reznikov were using. And by staring at it for such a long time, we figured out how to kind of localize the sum into the right regime with the optimal width, and able to improve on the exponent. Okay, then so I'm already out of time, but let me just quickly say what is cognitive hyperbolic bootstrap. So, actually, how much time do I still have? Zero. Okay. Well, anyway, the summary is that I've proved that if you use, let me just come back here. Okay, so at least for compact hyperbolic surfaces, the set of solutions of these equations, so thought of as equations for the OP coefficients and the spectrum, is precisely the set of hyperbolic surfaces. There's nothing more, nothing else, and the proof goes through Gelfand duality. Somehow the Gelfand duality tells you that once you have a committed associative algebra, it should be the algebra of functions on some space, and the meaning of these equations is that they implement associativity in the presence of conformal invariance, and then you get the G mod gamma. So okay, I'll just leave this here, even though I didn't explain it. Yeah, thanks a lot.
Questions? So you talked about upper bounds for spectral gaps. How about lower bounds? So there is a famous Selberg one-quarter conjecture.
Yeah. So the reason, so it may be possible to get lower bounds as well, but it will have to be more complicated method than what we use. So basically, we just used 4-point functions of fixed primary operators. And in a conformal bootstrap, people have been able to get also lower bounds by using systems of correlation functions. So keeping the external primary operators fixed, but also varying those. And actually, since Adve proved that the totality of the bootstrap equations implies anything that's true about the spectra of hyperbolic surfaces, in the compact case, so if you could generalize this theorem to also to the non-compact case, then this would be a proof that in principle the Selberg conjecture follows from the bootstrap. The Selberg conjecture is about congruence surfaces, so you need to generalize it to a non-compact case. Yeah. Okay.
Are there any further questions?
Ask a question I already asked you. What about higher rank?
Yeah, well, that's a good question. We haven't really worked on it, but in higher rank you have now these joint eigenfunctions. There's more than one Laplace eigenvalue associated. Yeah, it's going to be technically more challenging. I, in particular, don't really know what happens to this multiplicity 1 statement for the triple product, but I think it's should be looked at.
I rank it's not shouldn't be true.
Yeah, for the multiplicity, this multiplicity.
This one is the property of SL2R.
That's well, yeah, but for rank 1 and higher dimension, so probably there's finite dimensionality, which is good enough for us. And then the question is, when it's infinite dimensional, maybe you can still parameterize the space of the intertwiners somehow, and still use this positivity. But and there could also be special classes of representations for which the multiplicity is finite dimensional. But I think the statement is that in higher rank, for example, for discrete series, it's always finite dimensional as far as I know, even in higher rank. For holomorphic, if you take a tensor product of two lowest weight representations, then any lowest weight representation I think appears.
Which representation?
Lowest weight.
Lowest weight.
Yeah. Then it's I think it's still finite dimensional. Anyway, I don't know enough about this about the higher rank case.
Any further questions? There are no further questions, so let us thank the speaker again. Minutes break until 10.